So again, this one's a little different because it's asking more than we were doing before. So if we look at this question here, if we start with 5 grams of copper wire, what unit? So this is going to be the key to all chemistry problems. What unit do they want in the end for this question? Atoms. How many copper atoms? So that means we're going to be starting with grams and ending at atoms. Okay, when we look at the periodic table, here's copper. Copper is 63.55. What are the units of the 63.55? They are grams per what? Moles, right? The units of that periodic table are always grams per mole. Do you see the word atom in grams per mole? No. So therefore, the periodic table will never be helpful for the word atoms. Ever. Never. The periodic table can only help us with grams and moles. So we need something else that's going to help us with atoms. And if you remember, 1 mole of anything is 6.022 times 10 to the 23rd of that thing. So 1 mole of copper is 6.022 times 10 to the 23rd atoms of copper. So we're going to have to use, whenever we see atoms, so this is super important. Whenever we see atoms, we have to use Avogadro's number. So we have to use Avogadro's number whenever we're using atoms, okay? That's going to be super, super, super important, okay? So can you use molar mass with atoms? Never. Whenever you see atoms, do not look at the periodic table. It will not help. The only time you can use atoms, that's Avogadro's number. So if we're starting with grams, can we use the periodic table? Yep, we can, because the units of the periodic table are grams. So we start with 5.00 grams of copper. What unit has to go on the bottom? Grams of copper. And remember, this 63.55, that is 63.55 grams in 1 mole. That's how we could transform this 63.55 to this 63.55. So that means, does the 63.55 go on the bottom of this conversion, or does it go on the top? Goes on the bottom because it goes with the grams. So the number 63.55, the number on the periodic table always goes with the grams. On the top or the bottom of that is always 1 mole. So 1 mole of copper. So any questions on this piece right here? Okay, we're good on this piece. Now, the next piece, we cross off our units. Now we're left with moles. But what units do they want? Atoms. So we are left with moles, but we want atoms. So now we're going to use 1 mole equals 6.02 times 10 to the 23. So one of these is going to go on the top, and the other one is going to go on the bottom. Which one is going to go on the bottom? 1 mole or 6.02 times 10 to the 23rd atoms? 1 mole, because moles on top, so we need to put moles on the bottom to get rid of it. So that means that 1 mole goes on the bottom, which has a lot of room. And then on top is this giant number, 6.022 times 10 to the 23rd atoms of copper. So in our calculators, we've got a pretty big calculation. This is why we need our calculators in class, in homework, and everything all the same. So in your calculator, you're going to put 5 times 6.022 times 10 to the 23. So that goes on the top. And on the bottom is 63.55. So put this in your calculator because this is a tricky one. And you can do this, you can do just about anything in your calculators. Well, we don't have negative exponent in there, but this is a tricky one. So make sure you try to put this one in your calculator. Let's just see when it stops freaking out. See if I can fix this. So when we put this in our calculator, we get, here it is nicer. Tried to leave it room. So we end up with 4.74 times 10 to the 22 copper atoms. So did we get that? And again, if you don't have your calculators today, just make sure you're bringing them from now on. So again, make sure especially that you're getting this times 10 to the 22 in your calculator. So just again, so how you put this in your calculator is you take 5 times 6.022. Hopefully most of you have an E button, E23, parentheses, divided by 63.55. I know it's a little messy, sorry about that. And if you're not getting this number in your calculator, you need to come and see me, okay? We'll go over how to get these in your calculator if you're not getting this number. So you need to practice so you get this number again and again and again. Okay. So now we're going to do some more of these. Any questions on this? Yes. Okay. So again, if you're not getting this number in your calculator, come and see me. We'll definitely go over this. We can go after class today. We can go through to make sure you're getting the correct numbers. If you're getting one off here, so if you got like 21, 22, or 23, it's the way you're putting this number right here in your calculator. Okay, so we'll work on each calculator kind of has a different way that it works best to put an exponent in. And so if you're not getting the times 10 to 22, make sure you come and see me so we can go over and figure out which way your calculator likes to work best. Okay, so now here's one for you to try. Packet of artificial sweetener has 40 milligrams of saccharin. Here's the structural formula. Well, that would be annoying to add it all up. So look at, here's your molar mass. We gave the molar mass here. So we want to know how many molecules are in a 40 milligram sample, and then how many carbon atoms are in the same sample. So why don't you try, here's number one. Try number one. We'll do number two together. So you try number one. So we want to know how many molecules of saccharin are in this 40 milligram sample. So try this, and we'll go through this one together in just a minute. Okay, so we're starting with 40 milligrams, and we want to go to molecules. Right, so we're starting with 40 milligrams of saccharin, and we want to go to molecules, okay? All right, so starting with 40 milligrams, and we want to go to molecules. So we're going from milligrams. So remember 1,000 milligrams in 1 gram. So if we start with 40 milligrams, I'll worry about my sig figs in the end. Okay, so 40 milligrams of saccharin. I'm just going to call it sac, okay? Don't have to write the whole thing. What unit has to go on the bottom? Milligrams. Okay, so if we look at this conversion up here, one of these goes on the top and the other one goes on the bottom. Which one's going to go on the bottom? 1,000 milligrams or 1 gram? 1,000 milligrams. So 1,000 milligrams goes on the bottom. So on top must be 1 gram of saccharin. Okay. How are we feeling on this step? Good here? Okay. So now we have grams of saccharin. So let's say I have no idea what to do from here. What unit has to go on the bottom? Grams of saccharin, right? So grams of saccharin has to go on the bottom because we don't want it anymore, right? We want to get to molecules. That's where we want to go. So we have to keep going until we end up with molecules on the top. So we just keep going. Okay, so we have grams. Can we go from grams straight to molecules? Molecules. We can't go straight from grams to molecules, but where can we go from grams? We can go from grams to moles. How do we go from grams to moles? Where do we look for grams to moles? The periodic table. So do you see here they gave us this molar mass? Up in the problem, they gave us the molar mass. Look at the units of the molar mass. The units of the molar mass are grams per mole. So that line right there is the same as the line here. We just have to put it in the right arrangement. So on here, if we look at this, so here is either the top or the bottom, and then mole is either the top or the bottom. Which one are we going to put on the bottom? Are we going to put the one with the grams on the bottom or the one with the mole on the bottom? Grams on the bottom. And I did not leave a lot of room here. I'll be very careful. Oops. One. So it goes, oh, there, I'll just move it over a little bit. 183.18 grams over 1 mole of saccharin. Okay, how are we feeling about that conversion? Okay, a little bit. Okay, so this is just a metric conversion. Metric conversion. This we found from the periodic table. That's PT, was the periodic table. Now, if we cross off our units, grams crosses off with grams. Now we have moles of saccharin left. So the unit we have left is the one that's on the top. Did they ask for moles? They did not. They asked for molecules. How do we go from moles to molecules? Can we go from moles to molecules? We can. 1 mole of anything is 6.022 times 10 to the 23 of it, right? So that's our Avogadro's number. So if we have 1 mole equals 6.022 times 10 to the 23 molecules, one of these has to go on the top and the other one has to go on the bottom. Which unit do we want to go on the bottom? Moles or molecules? Moles goes on the bottom. So 1 mole is 6.022 times 10 to the 23rd. I know this is going to be a little weird. How they abbreviate molecules is MOLC. How they abbreviate moles is MOL. Just want you to see that now so you don't freak out when you see it online if you look at any videos. So molecules is MOLC and moles is MOL. So now in our calculators, it's going to be 40 times 6.022. I'm going to put an E times E to the 23. Parentheses divided by 1,000 times 183.18. So you gotta put all that in your calculator to get to our answer. So try that and we're gonna go over it in just a second. So here's the key, but again, I changed it to grams here. I did this before because I didn't have room. But in your calculator, if you put this in your calculator, you will get this answer. So don't forget, you're going to probably need parentheses depending on the calculator. It can get a little tricky. It can get a little bit tricky. Okay, so now the next question, because this had two parts, the next question was, good question number 2. Question number 2 said, how many carbon atoms are there in the same sample? So if we look at this, here's our, I'm going to look at this one right here because it's easier to see. Well, I guess we can look at right here. So our saccharin is C7H5NO3. How many carbons are in that? 7. So for every one molecule of C7H5NO3, there are 7 atoms of carbon. So you see how I just took that ratio? Because for every one of these, there are 7 carbons inside it. So we can say for every one C7H5NO3, there's 7 atoms of carbon. Okay, so that means if we have this many molecules, how many carbon molecules will we have? I mean carbon atoms, if we just want to get carbon out of there. What will we do with that number? Just to multiply it by 7. So if we have 1.31 times 10 to the 20 C7H5NO3, I always forget the S. And this is molecules. I'm going to write the whole word out this time. For every one C7H5NO3S molecule, how many atoms of carbon do we have? 7 carbon atoms, or 7 atoms of carbon, however you want to say it. Both are right. So when we do this, oh, well, here's the whole thing nicer. Exact same thing I just did. So when we do this, let me erase this one too so you can see this. This was 7 atoms for every one of these. What if they asked, what if the question said, instead of how many carbon atoms, what if it said how many hydrogen atoms right here? How would these problem be different if it said hydrogen atoms? What number would go on top? 5. 5 would go on top. What if it said how many oxygen atoms? What number would go on top? 3. Because there's 3. Oops. 3 oxygen atoms. So we're going to be practicing with this a bunch. So pretty soon, by the way, and why I'm so crazy about you learning about this with the units and so great, pretty soon, these conversions are going to be like 1, 2, 3, 4. You're going to have to be doing a bunch of conversions, and you're going to have a line. Like you'll have like, this will be conversions, this will be conversions, this will be conversions, and you have to keep track of your units. It really is the same thing over and over and over again. The only difference is going to be your units. So your units are going to help you figure out your math. So the units are the key to the chemistry math. So we're going to keep practicing this for the next 4 weeks. Okay. So now we're going to move on to something a little bit simpler. Empirical and molecular formulas. So the first thing we're going to look at is percent composition. So when we look at percent composition, percent always means the same thing. So if you took an exam that had 100 questions and you got 80 out of 100 questions, what's your percent? 80%. Because you took 80 divided by 100, and then you multiplied by 100, that gave you 80%, right? If you took an exam that had 10 questions, or a quiz that had 10 questions, and you got 9 right, what was your percent on the quiz? 90%. So if you had 9 out of 10 questions, then you multiplied it by 100%, which gave you 90%. So percents are always the same. It's always part. Let me write that one more time. Part over whole times 100. So on your quiz, the part you got right was 9 out of the whole, which was 10, and you multiply it by 100. It's the exact same thing in chemistry. So this next question here is a percent composition question. Part over whole times 100. So we have a 10-gram sample of a compound has 2.5 grams of hydrogen and 7.5 grams of carbon. How we find the percent composition? Part over whole times 100. So we've got hydrogen, percent hydrogen, and we have percent carbon. The part of hydrogen is 2.5 grams of hydrogen. What's our whole? Well, first of all, what's our part? Let's do this one part. What's our part of carbon? 7.5 grams of carbon. Now, this compound only contains carbon and hydrogen. So if these are our parts, how much is our whole? What's the mass of the whole thing? 2.5 plus 7.5. So our whole is just 2.5 plus 7.5. 2.5 plus 7.5. And then times 100. And that's how you do percent composition. You just take part over whole times 100. Figure out the part, figure out the whole. And this is 10 because it tells you when you add it up, it says 10 grams. So I'm just going to write 10. 10 grams. 10 grams times 100. Now, here's hydrogen. Hydrogen is 25%. If this only contains hydrogen and carbon, what's the answer going to be for carbon down here? If hydrogen is 25%, how much carbon must we have? 75%. So you can always check your answer on these because they always add to 100%. Now, it might not be exactly 100.0. It might be like 99.8 or 100.5, but you can always see if your answers are right for percent compositions because everything always adds to 100. So this is percent composition, part over whole times 100. Okay, so I want you to try this one. I want to know the percent nitrogen and the percent hydrogen in NH3. But wait, there's no numbers. Where are we going to find the numbers for nitrogen and hydrogen? Where should we look? Periodic table. That's where the numbers are in. I will help you with one of them. I'll help you with nitrogen. What is the part for nitrogen? How much does nitrogen weigh? Nitrogen weighs, if you look at our periodic table, 14.01. That one's got a lot of numbers on it. So nitrogen is 14.01. Okay, so we go through this. We get these two. This is what we got about and around. Now, again, for sig figs, this one, you just kind of keep it however many digits you use for your molar masses. So for each of those, I had 4. So then I used 4. If you use 1.001 for hydrogen, well, then you'd have 3 significant figures. You kind of get to dictate your own sig figs on these. So do you see how I used 4 sig figs here and 4 sig figs there? So I kept 4 sig figs here and 4 sig figs there. So you get to kind of choose on this one. Okay, so this is percent composition, part over whole times 100. The next thing we're going to look at is empirical and molecular formulas. An empirical formula is the simplest way to write something. The molecular formula is the way it actually exists on Earth. Okay, so do you see here is the formula for benzene, C6H6. We could divide each of these by 6, and that would give us CH. So the empirical formula is the simplest way to write it. The molecular formula is the way it exists on Earth. Sometimes, by the way, they're the same. Sometimes they're not. So if we look at this one, how could we simplify C2H4O2? If we divide all of them by 2, this becomes a 2, so we end up with CH2O. But what about H2O? Can you simplify that? Nope. Sometimes you can't simplify them. How about CaCl2? Can you simplify that? Nope. So sometimes the molecular and the empirical formula are the same. Okay, so what about C6H12O6? Can you simplify that? You can. What would that simplify to? CH2O. So if we divide them all by 6, look, we end up with the same thing as this one. So you can have multiple compounds that have the same empirical formula. It's just the empirical means simplest. So simplest means empirical. Now, how to figure out the empirical formula? There's a formula for it. So, and you kind of have to follow the formula. So step 1 is assume 100 grams. So if you have 20%, how many grams is that? 20 grams. Assume 100 grams. That's step 1. Step 2, convert everything from grams to moles. So that's what we were doing before, using the periodic table. Step 3, divide everything by the smallest number. Divide everything by the smallest number. And this last one, step 4, this one you don't always have to do. This is only if needed. So if needed, you multiply to make a whole number. So when you're doing your homework this week, write this down and keep this next to you. Star this slide. You have to kind of, it's a formula, and you got to do this formula in this order for empirical formulas. Okay, so you need to learn these 4 steps. Okay, so let's try. A compound is determined to contain carbon and hydrogen, and we want to know what is the empirical formula. So step 1, assume 100 grams. Well, they gave us grams, so it's already in grams. We don't have to do step 1. So if we've got carbon and we have hydrogen, we just write our grams of carbon, 1.71 grams of carbon, and write our grams of hydrogen. Okay, what is step 2? Convert from grams to moles. When we convert from grams to moles, where do we look? Periodic table. Right, so we look at our periodic table, and there's 12.01 grams of carbon in 1 mole of carbon, and 1.0, I think I used 0.08 in this example, 8 grams of hydrogen in 1 mole of hydrogen. And then we put these in our calculators. Now, when you're doing empirical formulas, don't round and just ignore the world of significant figures, period. Make sure you kind of keep 4 to 5 places past your decimal every time. when you're doing these, and you're going to see why in just a second. So if we put these in our calculators, we get 1.71 divided by 12.01. This one gives us 0.14238. See how I kept 3? You can, by the way, some people are like, can I keep all my numbers? Sure. You can keep every number you want. The next one's 0.287 divided by 1.008. That gives us 0.28472. Okay, so that is step number 2. What is step number 3? This is the step that everyone forgets. Divide everything by the smallest number. Okay, so which one of these is the smallest number? 0.14. So we divide everything by the smallest number. So when we do this, we divide this by 0.14238, and we divide hydrogen by 0.14238. We divide everything by the smallest number. So this one gives us 1, and this one gives us 14238, gives us 1.99. 1.9997. That is close enough to 2. So now we have 1 carbon and 2 hydrogens. What is our empirical formula? It is CH2. So first, assume 100 grams. Well, there is 100 grams. Then convert everything to moles. Step 3, divide everything by the smallest number. And then that's our empirical formula. So try this one and we'll go through it together. For chlorine, we have 5.31 grams of chlorine. For oxygen, we have 8.40 grams of oxygen. So step 2 says convert them from grams to moles. So we look at the periodic table, and chlorine's molar mass is 35.45 grams chlorine in 1 mole of chlorine. Oxygen is 16.00 grams of oxygen in 1 mole of oxygen. And again, here's where we don't worry about our significant figures here. So when we put these in our calculator, 5.31 divided by 35.45, we get 0.149788. And there's some more digits, but that's what we got. So we all got that? Yes? Okay, the next one is 8.4 divided by 16. And that is 0.525. Okay, so that is step 2. So step 2 said convert from grams to moles, right? So we converted from grams to moles. That was step 2. Now step 3 says we have to divide by the smallest. Divide by the smallest. Okay, which one's smaller? 0.14. So we'll divide both of them by 0.149788. Whatever you do to one, you do to them all. 149788. So this gives us 1. This gives us 3.55017. Okay, so here's where that step 4 comes in. So step 4 says multiply to get whole numbers. This 3.5 is not a roundable number. We can only round like 0.1 or 0.9. Everything else we need to multiply to get a whole number. So we need to multiply 3.55 times something to get a whole number. And I get questions all the time. People are like, what do I multiply it by? Start with 2. If it doesn't work, go to 3. If that doesn't work, go to 4. If that doesn't work, go to 5. Just keep multiplying. So let's try it. Let's take 3.55 and we're just going to multiply it by 2 times 2. Oh, I got 7.100. We can round a 7. 7.1, we can round to 0.1. So if I multiplied this one by 2, I also have to multiply this one by 2. Whatever we do to one, we do to all of them. So that gives us 2 carbons. So our empirical formula is Cl2O7. And this right here, this is the step 4. Multiply to get whole numbers. That's our step 4. And again, we can only round 0.1 or 0.9. The rest of them we kind of have to multiply to get a whole number. So we really work hard to make them not rounding, but sometimes you have to. So sometimes you have to. So in your homework, sometimes you're going to have to round. I mean, sometimes you're going to have to multiply. So this is empirical formula. So again, make sure you've got those steps near you when you're doing your homework because you need to follow those for each piece of it. Okay. Now, the next piece we're going to do is one more little step on top of it, and then that's the end of empirical and molecular formulas. This is the empirical formula, but we are talking about empirical and molecular formulas. So how do we find the molecular formula? So how we find the molecular formula? One more step. We take the molecular formula's molar mass over the empirical formula's molar mass. So we take the molecular formula's molar mass over the empirical formula molar mass, and that's going to give us a really important number. Sorry about my handwriting. Okay. Now, sometimes people are like, which number goes on top? Here's an important piece. This number on the top, it's always given to you. It's always in the problem. It's always in the problem. It's also always the bigger number. Always the bigger number, and it's always given to you in the problem. How do we find the empirical formula molar mass? Well, didn't we just find an empirical formula? How would we get the molar mass of this empirical formula? We would just add it from the periodic table, right? 2 Cl's and 7 oxygens. So how you get the empirical formula molar mass? You just add. You just look at your answer and you add. Okay, let's practice. A compound has an empirical formula of CH2O. The molecular formula or the molecular mass is 180. Again, when we see AMU, AMU also means what? Grams over moles, right? This is straight from the periodic table. This is just AMU is 1 atom, and this is a mole, right? So AMUs and grams per moles, same thing as the periodic table. So if we look at our formula, molecular formula, molar mass over empirical formula, molar mass. Which one's going to go on top? 180 or 30? 180, always the bigger one. 30 goes on the bottom, and that's going to give us a number. So if we take 180 and divide it by 30, it gives us 6. By the way, this number always works out perfect. You always get 1, 2, 3, 4, 5, 6, 7, 8. You don't get decimals here. It'll always work out perfect. So this 6 means we have our empirical formula, CH2O. We just multiply everything by 6. So we had 1 carbon. If we multiply everything by 6, how many carbons do we have now? 6. We had 2 hydrogens. If we multiply it by 6, how many hydrogens do we have? 12. If we had one oxygen, if we multiply it by 6, how many oxygens do we have? 6. That is our molecular formula. So it's only one more tiny piece. It's only one more tiny piece. You just take the big number, divided by the small number, and often this one will be given. This one you have to add from the periodic table. In this case, they gave it to you, but often you do have to add it. So there's only one little extra step. So again, empirical, simplest, molecular is the way it actually exists on Earth. Okay, any questions on empirical or molecular formulas? Feeling okay on these? Okay. Oops. So here's everything I just did, just neater. The same exact thing, just prettier. Okay,